at all. Okay, little earth science. Knowing the zenith is important. It helps us to first figure out the difference between solar south and magnetic south. They're different. If you take the compass and face magnetic south, at noon, the sun is going to be about 14 degrees off to the west of that magnetic reading. Well, that doesn't make sense because I thought that's south, but south is over there. Well, magnetic south and solar south are different. So here in Vermont, if you want to find the best orientation, take your compass, face south, turn to the right about 13 degrees. That's solar south, okay? It's different on the west coast, but here, magnetic south, turn to the west about 14 degrees, and that's where solar south is, okay? The more perpendicular the collector is, the greater it performs. The sun's rays come pretty straight, so the more perpendicular that angle is, the greater the performance. How important is it to face south? Well, in terms of production, I can basically face east or west and still get 77% of the expected energy. So there's solar south, let's say there's solar south, or well actually there's solar south, and I'm facing due west. My collectors will still get 77% of the expected energy if I were facing south. So that's not a deal breaker. If your house is oriented 90 degrees to the wrong direction, you're still going to produce over 3/4 of the energy. Maybe you add another collector or two to make the difference up. Okay? This is declination. This is what I was referring to, the difference between magnetic and solar south. Okay? So 15, actually I was wrong. 15 degrees, I would say. But, you know, what's 1 degree here or there? Alright, basically, just real quick, what this shows is this yellow spot is the sweet spot of orientation. This is where I want to put my collectors to get the most out of them. And if I look here at the orientation, these numbers here are the orientation. So I'm at 30 degrees to the east and 30 degrees to the west, and I can still get 100% performance. So if I'm 30 degrees to the east or 30 degrees to the west, or within that 60-degree window, I'm still looking at 100% performance. And these lines are the inclination, right? So I can be from 15 to 55 degrees. 15 degrees to 55 degrees, and I'm still looking at 100%, 95 to 100% production. So the bottom line here is there's a big window of opportunity. 60-degree different, and you're 60 degrees, and you're still at a 95 to 100%, and you have, well, 15 to 55, so 40-degree window on the slope, and you're still up at 95%. Okay? So if you have a question whether I should tilt my collectors up off the roof, my gut feeling is, without even asking what your roof pitch is, no. Put them flush. It's going to look nicer. It's going to work easier. You're not going to have mechanical issues. Put them flush on the roof. You know, I hate to say it, but aesthetics is one of the most important decisions that you can make with regard to installing these.
Higher pitch roof work better?
Well, it depends what you want the heat for. If you want the heat for wintertime use to heat the house, then a steeper pitch is better. But if you want domestic hot water year-round production, then, you know, anywhere from 30 to 60. But if your goal is to heat your house in the winter, then the steeper is better. All the way up to 90 degrees. Steeper is better when you want heat for the home, okay? There's a couple instruments you can buy. Not going to get into this too much for site surveys. Okay, basically, solar thermal is a closed loop. There's several different designs, but most of the designs in the U.S. are closed loops, right? And basically, we have this happens to be a closed loop with a storage tank. On the bottom is a coil for the solar. On the top is a coil for the boiler. So the solar supplements the boiler. When the tank isn't heated up to the necessary temperature, the boiler kicks in and heats up the top of the tank. It gives all throughout the day. This type of system gives the tank a chance to heat up from the bottom coil first. So we have, you know, radiation hits the collectors. The pump turns on, circulates the heat transfer fluid, which is normally a propylene glycol. right? We'll only use glycol so it doesn't freeze. And circulates through the collectors, pulls the BTUs out of the collectors, sends them down into the tank, and they move from the coil into the water, all right? And it continues the cycle. Now, here's a sensor at the collectors, a temperature sensor at the collector, and a temperature sensor at the tank. It's an automatic control. As soon as the collectors are hotter than the tank, the pump kicks on. When the collectors get to within 3 degrees of the tank, the pump turns off. This could go on and off all day long. The clouds move away, the clouds come in, the pump turns on, turns off, turns on all day long. But slowly what happens is the collector temperature and the tank temperature climb like this all day. At 8 o'clock in the morning, the collectors are 100 and the tank's 90. Then it's 105, 95, 110, 100, 115, 105. It keeps going up like this, incrementally. But if I look at a system, all of a sudden the collector temperature climbs like this, but the tank temperature stays down here, I know there's an issue with heat exchange and flow rate. So you always see the temperatures climb incrementally. Okay? Basically, oh, by the way, if anybody would like a copy of this, I'd be happy to give you a PDF, because there's a ton of information. I didn't make handouts, but if you don't have a card, I'll give you one. You can email me and I'll give you a PDF of it. Active or passive, direct, these are the adjectives for different types of systems. All right, I'm not going to go into that at this point really, because basically we're using a pump, so it's an active system and it's closed because we're using glycol. Okay. Now we can also use 2 tanks, so we can transfer the heat from one tank into the second tank. All right, there's a lot of strategies also using non-pressure tanks. In some cases, don't use any tanks at all. Right? We go right into the load. In my house, I don't have a storage tank for heating. The heat from my collectors goes right into my floor. So one of the things that probably more than 9.5 out of 10 solar thermal experts promote the use of big storage tanks. Because on paper it makes sense, big storage tanks. But in reality, after I, carefully studying the performance of a lot of solar heating systems, big storage tanks are not cost effective for solar hot water systems. Store the energy in the house, in the floor, in the walls, in the chairs, and everything that's in the house. That's where the energy needs to go, not into a storage tank. Okay, there's also a system called a Drainback. Now, a Drainback system is one that doesn't need glycol. This system drains back at night into a reservoir so that the water doesn't freeze. Right? This allows us to use water circulating through the collector. Now, it's still a closed loop, but it uses water as opposed to propylene glycol. The challenge is these collectors have to be tilted on the roof so that they slope downward, and all the piping has to drain. If it doesn't drain properly, obviously it's going to freeze. Okay? Some important things is, their drainback system. The bottom line is, drainback systems are more complicated than steamback, and they require a knowledgeable plumber to install. A regular system I showed you before, where we have a coil in the tank, that's something very simple. Most people can understand how that goes, and we can plumb that together. Residential clients don't generally do drainback systems. All right, here's the 3 types of collectors that are most utilized. Anybody familiar with vacuum tubes? There's vacuum tubes and flat plates down there. Different manufacturers. They're basically the same thing. All right. I used to be a vacuum tube guy, right? I used to be like, oh, these are the next best thing, and that's what kind of got me out of teaching, because vacuum tubes, they get hot, and it's impressive. If you're going to touch one of those bulbs, you burn your hands, and you still can't help yourself. You're like, nah, it can't possibly be that hot. And 350, 400 degrees, these vacuum tubes work well in the shade. They work well when they're not oriented properly. They work really well in the middle of winter because there's a vacuum, obviously, in the glass. But the flat plates, there's more surface area in the flat plates. So it makes up for some of the losses, all right? So I'll get to that point, but the bottom line for me is Doesn't matter what the guy tells you. He's trying to sell you a flat plate versus vacuum tube. It's all about what you feel comfortable with, because they both will perform equally well, and they cost about the same. There's always exceptions, of course, but generally you can't go wrong. Which one do you feel comfortable with? Which one looks better on your roof? All right, and then of course pool heaters, which I'm not going to get into too much here. What's probably going to happen in the future, though, for those of you who are thinking about this in 3 or 4 years from now, you might want to move forward with a system like this, is it's going to be some combination of all three, where we have a very low cost, very inexpensive polymer, EPDM, for example, very inexpensive, right? Where we have the heat loss coefficient is low in the vacuum tubes, and the surface area is high in the flat plate. And they're building a collector right now that uses the flat plate type of box, but it's the EPDM absorber. And the glass that's used is evacuated. So you're going to see a change a little bit. It really boils down to cost of installation. The materials costs are going to end up be about the same.
Is there a good manufacturer for the unglazed pool heater type?
FAFCO is probably a leader in the country. FAFCO. FAFCO.
Well, that's an adjunct to I get my hot water off the wood system during the winter, so
Well-
summer use or something.
See, these don't have any way to prevent heat loss. All right? So as soon as the temperature of this collector gets above air temperature, heat goes out of the collector real quickly. This would be the next step up, because it acts as sort of a greenhouse. It can go to 110, 120, 130 before it starts losing a lot of heat. Right? So for hot water systems, a flat plate would probably one of these two. This is generally just for pools, because it's only going to do well on hot days anyway. So, in fact, pool systems are tough to heat up here with anything other than, fossil fuel or electricity. In the middle of the summer, it takes a lot of energy to heat up a swimming pool. Okay, basically you tie it right into the swimming pool with the existing plumbing. Very inexpensive, but they won't work well when, even on a day like this, it's 81 or 82 degrees out. Well, if the collectors are 85, they're going to start losing heat before it goes into the pool, so they don't even work well on a day like this. A flat plate, as I mentioned, they were invented in the 1800s. There's not that much new to them, other than it's aluminum or copper with a glazing piece of glass that traps the heat in. Right? So basically, there's copper tubes that are welded to the copper sheet. The copper tubes are what the water is, or the glycol passes through, and it pulls the heat out of the sheet, the absorber. Right? And we can put a whole bunch of these in series and just increase the flow rate. There's different piping designs inside. This particular style is called a meandering or serpentine, where the copper tubing is winding back and forth. These are designed for small domestic hot water systems, because there's a lot of pressure drop. But the collectors work very efficiently with just groups of 1 or 2, but not any more than that. Okay. So this is a parallel flow versus the serpentine flow. This is what the piping looks like internally. All right. I'll tell you this: if you work with a manufacturer, I guarantee they're going to have a couple key features about their collectors that make theirs better. Right? Well, just take it, learn what you can about them, but there are really no new features that make their system any better than another. They might be different. They all do just about the same. The real thing is accessibility. Are they going to be delivered on time? Do they have a warranty? And are they certified? All right, flat plates are tough to put up on a roof with just 1 or 2 guys. So if you're thinking about installing it, helping out, you have a guy that is going to help you. Flat plates is going to take 3 or 4 guys to get these up on the roof. They're cumbersome. We need 2 ladders. We need a good staging area. All right. Once they're up, there's no maintenance on the roof, but you can't do it yourself. Vacuum tubes go up piece by piece. So you take the frame, take the feet, put 1 tube in at a time. 1 guy can do a whole vacuum tube system, no matter how big it is. Flat plates, multiple guys. Not for very long, but it's not. And in the wind, if it's a windy day, you can't get those things around the roof because you're carrying a sheet of plywood around. you know, a $450 sheet of plywood. That's you know, another thing about flat plates is you have to space them. And on a flat roof, they have to be, the rows have to be spaced about 12 feet apart. Flat plate, greenhouse type of stuff, heat loss, absorbers. An absorber is simply a piece of copper sheet with spray paint on it. Black or blue. The blue is the newer stuff. It's made of quartz, nickel, aluminum, and it absorbs UV rays, UVA and UVB. So the black absorbers do really, really well when the sun is out. The blue absorbers do really, really well all the time. Right? And you saw that picture of the facade in Austria. All those blue coated absorbers. They do really, really well in cloudy conditions. Now, vacuum tube collectors. All these come from China. And you know, you might find somebody online that says these are made in America. Not true. There isn't a single vacuum tube collector made in America. They modify a couple pieces of the equipment so that they meet the requirement. But the tubes are all made in China, and 95% of them all come from one factory. And I think just in China alone, there's like 350 vacuum tube manufacturers. Right? There's generally two kinds. If you go down to the solar store tent, you'll see one kind that has a fin inside of a big glass vacuum tube. Another kind, which is this style here. Now this is a vacuum tube, and I'll pass this around. The vacuum is not inside the space. The vacuum is inside the layer between the two pieces of glass. All right? Now the way this is produced is it's basically two glass tubes. One narrow diameter, one larger diameter. The narrow diameter tube is sprayed on with this coating. That's the inside. That narrow diameter tube is then inserted into the larger diameter tube, and they're annealed at the top. Okay? And then pinched off on the bottom. Now that creates a vacuum. The vacuum is something like 10 times 10 to the negative 5 pascals, some really, really strong vacuum, right? You couldn't apply a vacuum like that to the flat plates because it would cause the glass to just break. But being that it's cylindrical, it's equal pressure applied around so it won't break. And they're very, very strong. Longer ones, you can actually stand on them, you can sit on them. But if I take it like this and I shake it, then you get a different frequency and the inside will break. So they're delicate, but they're very, very strong. All right. Also, on the bottom here, you see this is called a barium getter. If the vacuum breaks for some reason, it could be a hairline fracture. This turns to a powdery white, depending on temperature, but pretty much instantaneously. Turns to a powdery white, tells you the vacuum is no good. Well, how strong is the vacuum? The inside of this glass tube can be 250 degrees, and there can be ice on the outside. That's a 1/4 inch. That's R64 in just a 1/4 inch. All right, so R64 in a 1/4 inch. R is usually measured per inch. That would be R256 or something like that. So it's an incredibly strong vacuum, and that's why we get the shortwave radiation coming in from 93 million miles away, hits that absorber, and it gets converted to long wave radiation. Well, long wave can't pass through a vacuum. That's why space is cold, because there's nothing out there for the long wave to conduct through. So in the absence of any conduction, there's no heat movement outward. And all the heat goes internally, and then up into the manifold and down to the tank. Okay? So here, I'll pass this around. This is called a twin tube. Okay. So you see the faulty tube here with a barium getter turned to a powdery white. Now, if you do have a bad tube, you hear a lot of people say, "Well, the tubes go bad." Well, to replace a tube is about $20, and all you have to do is pull the tube out and insert a new tube. So it's not a big deal. I mean, you generally, when you install a system, you're going to have extra tubes on hand. Manufacturer, if you buy a vacuum tube system from a manufacturer, you should insist that you get 5% extra tubes. All right, I know, for example, several companies do. One local, well, relatively local in New York, Sunmax Solar provides 5% extra tubes. I think most of the companies do. You should insist on that, because 5 years from now, if 3 or 4 tubes go bad, it could cost you $400 to have them shipped back up to you. So you have them shipped originally, and just count on some tubes will go bad, which is part of the deal. That's why vacuum tubes aren't as popular as flat plates. But the reality is they're easy to replace. Okay? This is just an example of the temperature. The red one is the temperature inside the manifold. Okay, so basically, I took an infrared thermometer. I can move over here. So it took a temperature inside the manifold, and it took a temperature on the glass. Okay? And I wanted to see at what temperature does the ice melt. So the ice actually melted about 940. At that point, the temperature was already over 200 degrees inside the collector, and there was still ice on it. All right. So some people will say vacuum tubes don't work well in the north because they don't melt ice. Well, ice doesn't do anything to stop the journey of those photons. They've just traveled 93 million miles through 15 miles of atmosphere, however many miles there are, and a quarter-inch layer of ice doesn't do anything to stop them. So it's true. Vacuum tubes don't melt snow and ice. But snow and ice do very little to prevent that vacuum tube from getting hotter. Inside a vacuum tube is a heat pipe. That's what transfers the energy. Okay? I don't have a heat pipe to show you, but it's basically a copper tube that is pinched off on both ends, and it has a little bit of distilled water. Okay? And that distilled water vaporizes at about 80 degrees Fahrenheit. So as soon as that vacuum tube gets up to 80, the water inside this copper tube vaporizes, and the steam rises up into this condenser bulb. And if you go down, can't remember the guy, Steve Blackman, I think, has a vacuum tube system here. The condenser bulb takes all that steam. That's why it's called a condenser bulb, because the heat radiates out, and then the steam condenses back down and rolls back down to the bottom, and so you get a convection cycle inside the heat pipe. And the rate of convection is equal to the amount of energy coming in. There's virtually no energy leaving the tube. So all the energy that comes in gets concentrated at this condenser bulb. And that's why those condenser bulbs can literally, I've set a few of them up on the side of a house before, and they just melted right through the siding. They just, it's really phenomenal how hot those condenser bulbs can get. Okay? There's other styles called direct flow. A heat pipe is the kind where we don't circulate water down into the vacuum tube. In this style, this is a different style. This is not a heat pipe. In this case, we're pushing water down through the condenser bulb and back up. Okay. There's also thermosyphons. Now, thermosyphons are a very inexpensive system where the tank is included at the collector. So there's a big tank sitting on top of the collector. You may have seen one of these before. It's the most common approach in China, is to have the tank outside, connected right to the collector. It's hard to use these and meet plumbing codes. We can't have open loop direct systems in the United States. We have to have an indirect system. So it sort of defeats the purpose. And these aren't necessarily certified either. The cost is much, much less, but they're not certified. Okay? It would be good for something off-grid, a cabin, somewhere that you can put it right on the ground. $1,000, you have a whole system. It's a great deal, but not for in town. So this guy put this system together all by himself. A 3-story house, he carried every piece up by himself. That's one of the nice things about vacuum tubes. Flat plates, you can't do it all by yourself. Okay? Another nice thing is, if you notice the glass tube, it's 360 degrees. And so any energy that passes between the tubes is reflected back into the back side of the glass. All right, so if you have a light or white colored roof, you're collecting all the energy back onto the back side of the collector. No matter what time of day it is, you're getting energy from the front and from the back. So vacuum tubes you can boost their performance up 15 to 20% by including a white colored roof, or a tin roof can boost the performance significantly.
What was that about wind load?
Yeah, there's virtually no wind load on vacuum tubes. Okay, so you can stand it up. If you have an area where you have high wind and you're tilted up off the roof, you don't have to worry about really fastening that as strong as you would a flat plate, because wind passes right through the vacuum tubes.
So there's no cover over
No. No. They're exposed. I've had clients in Oklahoma that had them, bombarded with hailstones. Just recently, they had a lot of hailstones, and they get deflected right off. They don't take basketballs, though. I can tell you that much for sure. Pardon? Vibrations can be tricky because the frequency of the inside tube is different than the outside tube, and they'll break around the rim. So that's where we had some issues when they go on trucks. They were traveling down the road and rolled around the thing, they were broken. The packages looked brand new. Alright, so this is my 2 cents on the difference between flat plates and vacuum tubes. And actually right down there you have a perfect example, a company, a flat plate company and a vacuum tube company. And they're going to both have their own pitches about why you should go flat plates and why you should go tubes. Okay? The cost of the total cost, the collector's only 15 to 25% of the total cost. The difference between vacuum tubes and flat plate costs are really negligible in terms of the whole system cost. You might have a $7,500 job. The difference of the actual collectors are about $300. All right, well, let's look at the production. It's in terms of BTU, dollars per BTU. That's what's important. Well, the flat plates produce more at noon, but the vacuum tubes do better in the morning, they do better at night. And so over the course of the whole day, it's sort of a wash in terms of production. Flat plates do better in the summer. Vacuum tubes do better in the winter. So there's always, you can always say this is better and that's better, but the reality is neither one is necessarily better. They all have their purposes. If I have a high wind load area and I want to heat my house with a high temperature heating system, I have to go vacuum tubes because vacuum tubes will give me higher temperatures. But I heat my house with flat plates. So you might hear the argument, you can't heat your house with flat plates. They got to be tubes. It's not necessarily true, right? So when somebody says flat plates are better, tubes are better, just try to figure out what exactly you're talking about because it's not that simple. Installation costs are comparable, service costs are comparable. Aesthetics is really what it boils down to. Which one actually looks nicer? And some people like the tubes because they're newer. But it turns out they're not really any newer. Vacuum tubes were invented in Ohio in the 1970s with a Department of Energy grant. And the United States market didn't accept the vacuum tubes, so the guy went to China in the mid-70s, and the rest is history. But the life expectancy of the whole system goes to flat plates. Okay? There's less that can go wrong with flat plates. If the vacuum breaks, if the condenser bulb fails, flat plates pretty simple. All right? And that was the deal breaker for me. When my house 2.5 years old, it was a very important decision. Right? One of the most important decisions I made in the whole house. And I went with flat plates. And I've been really, really happy with it.
What would the numbers be though? Is it like 5 years from now, 10 from the other?
Well, I can expect a flat plate to produce heat if I service my system properly for at least 30 years. Vacuum tubes will do the same. The difference is I have over 6 or 10 years, I have to replace some tubes, right? But there's so many what ifs, and it's really just what do you feel comfortable with? If you're going to do it yourself, vacuum tube is going to be so much easier to do, and you'll be really happy with the performance. That vacuum tubes, they crank, so to speak. That's what they do really, really well. Especially if you can increase the reflectivity behind the tubes. That's when you start to make a difference. Okay? Aesthetics, some people like the look of flat plates, some people like the tubes. It's really up to the eye of the beholder. All right? Flat plates, though, you can get some nice flashing. The shingles are removed, and the collector becomes part of the roof, and it's all flashed around. Looks like a skylight. So you see some high-end homes, where all they want is something that looks really, really nice. They're probably going to go with flat plates. Okay? This is the efficiency curve of those 3 types that I'm referring to. The unglazed collectors, the flat plate collectors, and the vacuum tubes. All right? The unglazed collectors do better. Now down here is the difference between collector temperature and air temperature. So in other words, 0 would be where the collector temperature and the air temperature are equal. Under that condition, the unglazed pool collectors do better. Okay? But once the air temperature begins to drop, the efficiency goes to vacuum tubes. Vacuum tubes clearly do much, much better in cold climates. There's no doubt about it. Okay? But that's also relative. This isn't strictly air temperature. This is air temperature and this is collector temperature minus air temperature. So we could say also that if I keep my flat plate collector temperature down in the winter, they're going to perform equally well. So my heating system, if my collectors are producing 90 degrees, I can heat my house with 90 degrees. With most systems, the collectors have to be 140 before I can heat the home at all. Right? So the lower the heating requirement, the higher the efficiency of the collectors. The only thing you can do to change this, other than move south, is lower your heating requirement. Some of you prefer to move south. I gotta move north though. This global warming crap is killing me. I swear, I'll be up in the Green Mountains are nice though. I haven't spent much time over here, but the Adirondacks are they're awful nice up there. The SRCC is the certification for all the thermal collectors. So if you're going to search out some collectors that you want to purchase, they have to be SRCC certified in order to get the tax credits, which are significant. Okay, so SRCC is sort of like the UL. If you're going to buy collectors, they have to have the SRCC sticker, and they give you a chart of how much energy you should expect for these collectors. Manufacturers don't make up the numbers. The numbers that manufacturers give to you in terms of their production have to come from SRCC, which is an independent testing company, right? So it basically allows them to compare apples to apples. Now, yes, ma'am.
Do they like test independent ones?
What do you mean?
Like if somebody were to,
Yeah.
you know, start a small company
Yes.
or something.
They will. It's not cheap. In my experience, it's in the 10,000 range.
So there's no like independent one for like people who want to have their own system tested?
That would be more of like there are some outfits out there like university labs. There's also other testing companies, but it wouldn't come with the SRCC certificate. But I think you might be able to find somebody that will do it.
Yeah, but I was just saying like, if you want to get the tax credit, you build something
Oh, no.
yourself.
No, it has to have SRCC, and that is the $10,000 price tag. So thermal, I should have started with this. We're making BTUs. All right, it's all about BTUs. A human produces 500 BTUs an hour. The sun per square foot gives us about, right now, today we're probably looking at 1,800 BTUs per square foot. That's hitting this roof. That's a lot of BTUs. If you add up the square foot of this roof, say it's, 200 square feet times 1,800, we're looking at 360,000 BTUs today. Just hitting that roof right there. So that's where I'm talking about. We're wasting BTUs. Everybody buys BTUs. You buy your BTUs from an energy provider. Meanwhile, there's more BTUs that hit your roof every single day than you need. So it's all about BTUs. Ironically, the British don't even use BTUs anymore. Why? Because you don't just move the decimal place over to the left or to the right. We have to multiply it by 3.1, 3.17, and then we finally come up with numbers that we need, and we multiply by all sorts of coefficients. But basically, we're still using BTUs. One BTU, if I take 1 gallon of water, to heat 1 gallon up of 1 degree of water takes 8.3 BTUs. So that's how I can calculate the number of BTUs my hot water tanks. The temperature change times the volume times 8.3 equals the number of BTUs. Okay? So I'm going to go over different components real quick with the collectors, the tanks, the exchangers, controllers. Anybody have any questions? give me an approximate time. Were we like an hour and a half an hour? Man, over about 10%. So I don't know what you guys got planned for the rest of the night, but okay. Thanks.
We have to call security in 5 minutes.
Fair enough.
Get you out of here.
Yeah. Do that. It won't be the first time. There's so much that that's important. It's hard to trim out what you don't want to know because you want to understand the big picture, right? The placement of where that expansion tank goes in the loop makes a huge difference. A boiler installer puts the expansion tank behind the pump, but the expansion tank serves a completely different purpose with thermal than it does with boiler hydronics. The expansion tank helps to pressurize the pump so it doesn't cavitate. We don't have that problem. We're operating in a high pressure anyway. What we need that expansion tank for is when the collector begins to overheat. The volume has to enter the expansion tank. So one nice thing over the last several years, not even that many, guys were just buying this piece and that piece and that piece, and they were putting them together down in their basement. And they're all sorts of pieces. And now you see these nice little compact pump stations that include all of the pieces that you need. And again, there's a pump station down there that you can take a look at. But you got flow meters. This is actually the most important piece, is the air vent. Because if you don't get the air out of the system, it's going to cause the pump to overheat. And I used to do service calls, and my phone would ring, and I'd say, "You have air in the system. Hi, this is Todd. What can I do for you?" Because 9 out of 10 calls were too much air in the system. How do we get the air out? Because it would cause the pump to fail. And when the pump fails, the collectors overheat. And when the collectors overheat, everything, oh no, things are going to blow up. Pressure relief valve blows. They didn't put the expansion tank in the right place. So all sorts of problems just because they didn't get the air out. Okay? So that's a critical piece here, is getting the air out. Obviously, pressure relief valve, it's a closed loop. All closed loops need a pressure relief valve.
Where do you want to see the expansion tank?
I want to see it, it would be downstream or above the pump. In front of the pump, between the pump and the collectors.
Okay, so on the way back to the cool side.
On the way back to the collectors, correct. Between the pump and the collectors on the cool side. I'll show you a diagram that has that. Because when the collectors overheat, that's another very common misconception is collectors can't overheat. They're designed to overheat. It's okay for them to overheat. I hear people, oh no, the collectors are overheated. They burned. We have to replace them. No. That's what SRC tests for. It's called stagnation. They're designed to handle 350, 450 degrees. That's not the issue. The issue is the glycol overheating. All right? So how do we prevent the glycol from overheating? Well, the glycol can't be in the collectors when the collectors are that hot. Well, how do we empty the collectors when they're that hot? We don't. We let the laws of physics do that for us. Boyle's law, when the temperature of the glycol increases to a point where the boiling point has been met, then the water boils first. The water creates steam, increases the volume by 1,000%, increases the pressure inside the collectors. That pressure pushes the glycol out of the collectors. Where does it go? Into the expansion tank. Therefore, the collectors are full of steam. They're 350 degrees, and everything is perfectly safe. 350 degrees? Yes, that's what they're designed for. Okay? So collectors do not overheat. But if my expansion tank is too small, then all the collectors they don't empty properly. Then I burn my glycol. If the expansion tank's in the wrong spot, I burn my pump out because I got that hot fluid moving down. It's got to go in the expansion tank first. That's why I put it between the pump and the collectors. All right? So there's a lot of little details that make a big difference. So pump stations are the way to go now. Everything is concluded. Your flow meter, your sensors, the controller, the expansion tank port is right here. Right? This flow is going this way. So here's the expansion tank port. There's the pressure relief valve. I got my fill and my drain. That's how I fill the system. There's check valves. There's a flow meter here. The controller's automatically built in. Basically plug and play. And no matter what, there's lots of different manufacturers of pump stations. They're all really easy. Mount them to the wall. These two go to the tank. Those two go to the collector. Done. You don't have to go shopping around for any of your parts, and maybe you put them in the wrong spot. And we're not reinventing the wheel either. Guess where these pump stations come from? Germany. Guess who has been using pump stations for about 20 years? Germany. We're just catching on. It's neat. All of a sudden it's new. It's like, wow, this is new. No, not new.
That was a plug there that needs how much electricity?
Yeah, this is at full speed. At full speed, that's about 94 watts. Yeah, medium is 54, and then it goes down to 36, I think. But about 94 watts. 5-6 hours a day or so. I'm paying 13-14 cents a watt, or kilowatt, sorry. Okay, now there's two types of tanks. Basically, a pressurized vessel. Pressurized tanks are maintaining the home's pressure in the system, 50 to 60 psi. Or a non-pressure vessel. It's just a big open tank with a top on it, but it's non-pressurized. All right, and it's a battery. So you think of both of these as batteries. A real common issue with photovoltaics that everybody talks about. Oh, the battery's not going to work. How are we going to store all the energy when we need it in the nighttime, stuff like that? Well, it's not a battery in that sense, but it's a storage of BTUs. Okay, so we need to put those BTUs in a tank. Well, the more BTUs I put into this tank, the hotter the temperature. The hotter the temperature is, the lower the efficiency of the collectors. So it's a very fine line between a tank that's big enough and a tank that's too big. If it's too small, the tank temperature is going to skyrocket, my collector efficiency goes down. If it's too big, then my return on investment goes down because I'm never able to achieve the necessary temperatures in the tank. Right? So when it comes to a domestic hot water system, it's very simple. It's very straightforward. It's about 2 gallons for every square feet of collector. 2 gallons of storage per square foot of collector, you're good. But when it comes to heating systems, it gets real tricky, right? And in my experience, big storage tanks are overrated for heating systems, right? So don't let somebody talk you into a big, huge storage tank because it's not going to work out the way you wanted it to. Storage sizing considerations, anywhere from 1 gallon per square foot to 2 or even 3 gallons per square foot, depending where you live. Southern California, they can have 3 gallons of storage per square foot of collector. Here, we're better off at about 2. 2 gallons of storage per square foot of collector, right?
You're talking about domestic hot water now?
Yes. Yeah, there's really no good rules of thumb for heating in terms of storage. It's too complicated. Okay? Storage tanks, a lot of them nowadays have 2 coils. A coil on the bottom and a coil on the top. The coil on the bottom is dedicated for the solar. Why do we want to put the solar in the bottom? It helps heat the whole tank because heat goes up, right? Heat rises. Well, actually, that's a misconception. Heat doesn't rise. It's displaced by the more dense colder that's falling down. So it won't just go up. It has to be pushed up. So you get stratification. And so that means that the bottom of the tank is the coldest. Remember we looked at the collector efficiency? The higher the collector efficiency, the collectors can work more efficient when they're operating at a lower temperature. So we always want to introduce the coldest possible part of the tank to the collectors. That's going to cause them to constantly try to play catch up all day long. They're never satisfied. The collectors should always be working, trying to catch up. They never do. Unfortunately, I feel bad for them, but they're working hard. Non-pressure tanks are pretty. You can build your own. I know a guy who got a septic tank, 1,000-gallon septic tank. Put blue foam on the inside, put EPDM on the inside of that, and then he has 1,000-gallon storage. Well, in that case, it was very inexpensive to do. So now it starts to make a little bit more sense for big storage tanks because he's able to bring the cost way down. Right? So you can build your own non-pressure tanks. Some people will, Cornell University just built a building on top of a storage tank that was the size of a pool. They put concrete on top of that, and all summer long they charge that pool up with heat. And then in the winter, they bring it back out. But, from concept on, you can do it that way, but not as a retrofit. Not going to talk much about here, but for domestic hot water pumps, they have to be bronze and stainless steel or lead-free. Drainback systems, again, it's a little bit complex. I'm not going to get into for homeowners, but basically, when the pump turns on in a drainback system, it has to overcome this entire vertical head. So the pump I use for a closed loop system is different than the pump I'm going to use for a drainback system. Because in a closed loop, I'm basically just circulating from the, just circulating. But in a drainback, I have to pump it like a fountain, 30, 40, 50 feet in the air. So it requires a much stronger pump. Okay? Pump location for drainbacks is important. Now, the piping that you're going to use can basically be one of two types. All right? There's one exception I'll talk about, but basically one of two types. Copper or flexible stainless steel. It's got to be able to handle really high temperatures, okay, and high pressure. PEX tubing, it's not acceptable. Any type of plastic, certainly no PVC, anything like that can't handle the high temperatures. All right, so it has to be copper or flexible stainless steel. And I've been using a lot of flexible stainless steel lately. It's so easy to work with. You can run it over the eave, down over the doghouse, wherever through the basement window, around the furnace, and plug it in. And you don't even have to think about it. With copper piping, it requires a little bit more finesse, which some people have and some people don't. Cost comparison in terms of the much higher upfront cost. It's about $11 a linear foot, but you get the supply and return. Now you also have to consider though that the installation cost is the biggest cost in the whole thing. Is really the labor involved, right? That comes way down, not even close. But also, a flexible stainless steel is pre-insulated. So you've already got insulated jacket, but you also have not only the insulated jacket, you have the UV film around the outside of that insulation. And there's a sensor wire embedded in the insulation that you can plug from your controller up to the collectors. So installation cost, flexible is so much cheaper, but upfront cost, copper is cheaper. There's some installers that swear by the Pro Press and real quick and easy ways to use copper, but more and more the flexible line set is the cheapest way to go. But be careful, because they sell line set, then they also sell the connections, these brass connections. Well, $11 a linear foot for line set's not so bad, but every one of these is $15. And how many do you need? Do you need 8? Do you need 16? So just make sure, you'll find people that sell lots of different types of line set. How much are the connectors? And how readily available are they? Do you only have 5 in stock and they discontinued them? Because you'll never be able to find another one to fit. You can't just go down to your hardware store and get these connected. They're called quick connects, right? So you have to understand the cost with the connections.
How flexible is it?
You could tie it in a knot. You can't crimp it. You could roll it, do a pretzel knot, pull as tight as you want.
You can go around a tight corner, but
It could be inverted. You could wrap it around. Yeah, I couldn't think of anything more convoluted than a pretzel knot, and then you could do a pretzel knot. So, but the more convolutions you have, the harder it's going to be for your collectors to empty. You want them to empty for steam back. So it's real flexible. Like I said, it's got the sensor wire embedded in there. That's going to get your connection between the controller to the panels, right? I'm not going to talk about balancing a system, but if you have multiple panels on the roof, it's very specific the type of flow rate that you want, right? Manufacturers require a very certain flow rate, and if you don't get the right flow rate, they're not going to perform the way they're supposed to. But if I have 2 separate banks, one of them's getting 3 gallons a minute, another one's getting 1 gallon a minute, you're getting too much on this one, not enough on this one, so your whole system's not going to work. So you have to balance the system. And always think symmetry. Symmetry. And don't install a prime number of collectors other than 3 and 1 and 2. 1, 2, and 3. But not 7. Because you can't break 7 up into 2 equal banks. Not 11. Not the rest of them, however many there are. They have to be symmetrical. All right. Now, if you have, let's say you have 3 collectors. You want to mount these collectors on your roof. Are you going to put them in parallel? 1, 2, 3 on top of one another so they each have their own flow? Or are you going to put them right next to each other? 1, 2, 3. So you can put them in series, or you can put them in parallel with one another. If you don't understand series and parallel, I'm sorry. You know, I don't have time. But basically, do you want them to all run in the same string, or do you want to have 3 separate strings? And it's really a difference of what temperature are you looking for. Because series will give you a higher temperature. Parallel will give you a higher efficiency, though. Because if every collector is created equal, they also produce the same. But if I put 1, 2, and 3, well, 3 is going to be less efficient because it's getting preheated water. But if I have 1, 2, and 3, then all 3 are getting the same temperature. They're all going to produce at the higher efficiencies. So it's a trade-off. High temperature with series, high efficiency with parallel. Okay, now, what size diameter pipe do you use? Well, that's dependent on the square footage of collectors. Okay? That's and one thing you have to be careful about is you can't say you got a 3 collector system or a 7 collector system or 8 collector or 1 collector. How big is it? It's a 20 square foot system, a 40 square foot system. With thermal, I can't just say it's a 1 kW, 2 kW, 4 kW, and you can't say a 3 collector system because you got 20 square foot collectors, you got 30 square foot collectors, 28 square foot collectors, 21.75 square foot collectors. So the square footage is what's important, not the number of collectors. And the square footage of the system is what will determine your flow rate. The flow rate is what will determine your pipe diameter. Okay? And this is where any plumbers? Well, plumbers generally will send, 8 gallons a minute through a 3/4 inch pipe. That's what they're taught, and that's fine. That's cold water. Well, the hot water will increase the corrosion and erosion of the pipe. So it has to be down like 3 feet per second. So now I can do about 3.5 gallons a minute through 3/4 inch pipe above 140 degrees. Otherwise, in about 5 years, the copper is going to erode away because the abrasion of the minerals and the copper. The use of deionized water also, just to bring that up. I just ran into this issue yesterday. Somebody has a deionizer in their house, and they're running their potable water through a copper coil. Well, it's deionized water. And deionized water has very low ion content. Copper has a high ion content. And what happens with a high ion to low ion? The ions come out of the copper and causes the copper to erode and corrode quicker. So be careful about using deionized water in your copper coils. It's going to increase the rate of corrosion. Right? This is a storage tank. These gentlemen are down in the Bahamas. This is a 4,000 gallon storage tank with these copper coils, and they're all tied into their domestic hot water system. Now they got about 60 gallons a minute. And you think, well, why are we using 60 gallons a minute on those 3/4 inch coils? Why don't you use 1.5 coil? Why don't you use bigger coils, wider coils? And even so, the answer is it's surface area to volume ratio. So a 3/4 inch coil is always the best coil, no matter what your application is. The question is, how long does that coil have to be? All right. So, and I'll give you just a good rule of thumb that's always worked for me for copper coils is 1 linear foot of 3/4 inch copper coil per square foot of collector. Okay, it's a 1-to-1 ratio. 1 linear foot per square foot of collector. 1-to-1, linear foot of copper coil to square foot of collector. Okay, so you've got coils on the inside, or you can have external heat exchangers on the outside. The external heat exchangers on the outside work more efficiently because there's flow on both sides, but they require a separate pump. So now you add 2 pumps. I like simplicity. So a second pump may sound like a good idea because you're getting higher efficiency at the exchanger, but now you have twice the potential failure rate of 1 pump. Now you could have 2 pumps go bad. And if the second pump goes bad, then the system shuts down. You may not know how to fix it. Weeks go by. You're losing $2.50 every single day. My dad installed the system several years ago, and he's got it down. Looks in the newspaper, the UV index. He knows this is a $2.30 day. This is a $3.10 day. He knows exactly what his savings are every single day. He thinks he knows anyway. There's a big difference. One thing though is important when you're, yes sir.
I'm sorry I came in late, but when you showed that big tank there and
Yep.
the binder, what was that binder made of?
That's EPDM.
Okay.
And
What's the maximum safe temperature for that?
well, 184, but I recommend 175 where we shut off the pump. So 184 is the high temperature of the EPDM. When you design heat exchange in your system, always think counter current flow. Okay, always think counter current, and that's where it's counterintuitive to what you might think. When you want to put heat into the tank, right? You think you want to put heat right in the bottom of the tank. Well, the natural flow of heat is upwards, and so you got to bring your heat in the top and work down. So you always go counter current in every application. You go counter current. All right, now I wanted to show you this product because this is pretty unique. And by the way, if I didn't mention already, I'm not here selling anything. I have nothing for sale. But I did want to show you this. This was a patent several years ago in California, and it's a really good application for homeowners for domestic hot water because it allows you to install a system on your tank rather than buying a separate tank. All right. So this allows you to turn your existing tank into a solar storage tank by putting this heating element inside the hot water out of your tank, right off the top of the tank. It threads right off to the top of the tank. All right. Now this becomes your hot out. Normal plumbing goes off to your fixtures, and these two are your supply and return to the solar. All right. So if somebody has a small water closet, they don't have room for a second tank. You want something very inexpensive. You want to get a collector, a pump, some line set. You don't want a second tank. You put this right in your Ream 50-gallon tank, your A.O. Smith tank, whatever it is. You put it right in the hot water out, and now you turned your tank into a solar storage tank. It's called the Butler Wand. This old guy, he turned out to be a friend of mine, but he invented it several years ago in California, and it's a real effective heat exchanger. It's a bit pricey. I think they're in the $500 to $600 range, but it sure beats buying another tank. And they work well in different climates, but basically it's a tube within a tube. There's 4 layers. It also has glycol leak detection. So if the glycol system leaks, it'll be indicated before it leaks into your system. So there's basically 1, 2, 3, 4 layers of copper. So it's a double-walled heat exchanger, right? The solar supply goes down out the bottom of this tube, which spills out into this and coils back up, and then it comes back up through there and then back up to the collectors that way. So I'll pass this little guy around. This is called the Solar Wand.
You said you need a foot of oil per square foot of collector.
This is not the same ratio. This is basically whatever size tank you have. There's different heights. If your tank is 36 inches, 48, this is only for domestic hot water, not for heating.
But still, you wouldn't cover a lot of square footage on the collector.
No, this is obviously a demo unit, but a 36-inch will cover about 20 square feet of collector, which is good for 2 people. The biggest he's got, I think, is a 52-inch, and that's going to cover about 40 to 50 square feet of collector. Roughly 10 square feet per person. 10 square feet of collector per person for domestic hot water. And in Vermont, we're looking at about 55 to 60% solar fraction, right? You can check that out. It's called the Solar Wand. Okay, you can see how that gets plumbed into the storage tank and radiates the heat out through there. It's a real. There may be issues with areas of hard water, right? That might become an issue if there's high water content. One thing I want to point out about heat exchangers is the second law of thermodynamics is what's applied to this. Because every time you transfer energy, what happens to it? Less and less and less and less and less. The same principle. If I apply a heat exchanger between my solar loop and my domestic loop, that heat exchanger is a point of loss. We call that a performance penalty. Well, if I have one heat exchanger, I'm going to lose 5%. If I have 2 heat exchangers, I lose 10%. If So every heat exchanger you have in the system causes you to lose performance. Okay, so you want a design system that had the least amount of heat exchangers. Propylene glycol is required, not ethylene glycol. It has to be rated for high temperatures. Also has to be rated for freeze protection. Okay, so no ethylene glycol. The controllers these days are pretty user-friendly. Basically, they look at the temperature of the collectors compared to the tank, turn the pump on. But they can also regulate the velocity of the pump. And it's not just 100%. Okay, it's going to run at 30% or 70%. Whatever is coming in as insulation, the pump will respond according to the controller. All right. There's also data logging capabilities. Mounting, tilt mount. Go over this. Can somebody tell me what time it is? Okay, good. Thanks. We're doing pretty good. All right. This is the house that I built with the collectors not flush on the roof but tilted upward because I wanted to put heat into the house, not just domestic hot water. So the steeper the angle, the greater the tilt. Or I'm sorry, the greater the energy in the winter time. So drainbacks, they have to be tilted on the roof. Okay, this is actually up this way, but you can't really tell. But that's got a pretty big tilt to it. And drainbacks are more efficient because drainbacks allows you to remove a heat exchanger. Right? So I could pump to my collectors right down directly into my floor and then back up to my collectors because I'm pumping water. It's going to drain back at night. All right, which means more efficiency because I was able to remove a heat exchanger if I did a drainback. But I chose not to do a drainback because of aesthetics. Drainback systems have to be tilted 1/4 inch per foot. So if you mount them on your roof at 28 feet, turned out to be a 7-inch drop. You know, and you spend all this time to make everything all nice and straight and square and level and plumb, then, you know, and I decided I didn't want to have to explain myself to a single person about why my collectors are crooked. So I went with a steamback for that purpose. But drainbacks will produce more energy. They're just a little bit trickier to install. Why will drainbacks produce more energy? Because there's one less heat exchanger. They don't have that performance penalty. You know, here's a system with a drainback. You know, see, it's crooked. So somebody drives down the road and they see a crooked collector in the house and they wonder why. There's a very good reason why, but that person doesn't know. Mounting to the roof. The National Roofers Contracting Association says all penetrations must be flashed. Okay? In fact, I think you'd have trouble with insurance if for some reason something happened to your roof where it was leaking and you did not flash it properly. Okay? If it's flashed properly, insurance will cover it. But if it's not flashed, so no roof penetration can be left unflashed, basically. All right? Now, the whole idea of sizing a system, designing a system, is so that it doesn't freeze, it doesn't overheat, and then it gives you the best return on investment. Now, return on investment is a tricky one because somebody might spend the first 4 years paying off the system, and by the halfway through the 4th year, the system fails. So now they didn't get a return. Their return on investment was 0. All right. So, as I mentioned, you know, having a properly designed system and properly installed system is extremely important because anybody can make a system work for a few years and it looks great, it does well, everybody's excited about it. But when the system finally gets paid off, you want to make sure that you get your return back, and that's where you go from year 5 to year 25. That's where the real savings happens, right? So as I mentioned, total solar fraction is important to consider because bigger is not better. All right, there's a fine line between increased solar fraction and decreased efficiency. So in this area for domestic hot water, 45 to 55% is good for domestic hot water, 60% maybe. Heating is going to be much less. Solar fraction is the total solar production divided by the total load. Okay, a couple rules of thumb. The higher the temperature requirement, the lower the utilization. So you might be considering changing your heating system from baseboard to radiant floor. If you were to go from baseboard to radiant floor, that would be a very good first move because you're going to save money right off the bat anyway. But in terms of utilizing solar, you've lowered your temperature requirement. It allows you to use more of those available BTUs at a lower quality, a lower temperature.
Those have lower temperature radiation now.
They do. They have high efficiency baseboards, double stacked or wall hung ceramic and porcelain, high efficiency, low temperature heat dissipators. High solar fraction means low efficiency. This is why solar thermal is a supplement. It's not going to replace your existing system. It's a supplement. So the closer you get towards 100%, the lower the efficiency is. All right? Because if I achieve 100%, that means I've sized up a system so that I can achieve 100% of only one day. Because there's only one day that is the worst day, and that's where you have to achieve 100%. Every day thereafter, my system is 100%, 101%, 110%, 120% bigger than it needs to be. All right? So also, never exceed 100%. We don't want the system to overheat. The collectors can handle the stagnation, but we don't want it to if we don't have to. All right? We also need to know consumption versus production. In other words, what time are they taking showers? What season are we? Have a summer camp. Perfect opportunity is a summer camp where they have 500 kids a week. Everybody's taking showers from late May to late September. That's perfect. And then in the winter there's no load. So that's a perfect opportunity because if you looked at the graph from January, February, March, April, May, June, you looked at the graph, and if most of the graph was in the summer, well, where their load is, well, where's the production most? It's in the summer. So you want to match production and consumption if you can. Okay. Okay. Collecting, extend overefficient, never overheat. Couple subtle things there. Okay, so small residential hot water systems, generally 10 square feet per person for hot water. Okay, and that the average I think is cited for like Albany, New York. Very similar to the climate, but 10 square feet per person is going to give you about a 50% solar fraction. Does that mean you can install a 10 square foot collector if you live by yourself? Yeah, they make small collectors. You sure could. It wouldn't necessarily be the best investment because an additional 10 square feet is not going to be much cost. Most of the cost is in your tank, your piping, and all that stuff. All right. Now, for domestic hot water purposes, most generally it's about 20% of the total fuel bill. Okay. And if you have a 5-person home, what is my total gallons per day? Well, the national average is 20 gallons per person for the first 2 people. The third person is 15 gallons, and then the fourth person is 10. Okay? For large commercial domestic hot water systems, there's some formulas we can use to size up pretty easily, but basically we need to know the BTU load. All right? So I'm not going to get into that unless anybody's particularly interested. We still got quite a ways to go. All right, heating systems. So the 3 basic types of heating systems that are used with solar thermal are the radiant, forced hot air, and radiant baseboard. So was anybody familiar with a forced hot air system tied into solar thermal? A lot of people have furnaces. Those furnaces, the blower kicks on, the house goes like this, and then it contracts. All winter long it's doing this, like an accordion. The air gets hot, expands the house, and then the heat leaves, and then the house contracts, pulls cold air back in. So all day long it's just doing this. So for those of you who have forced hot air systems, you can hear when the furnace kicks on. Well, inside that plenum, we can put a radiator, similar to your car radiator, and hook that up to the solar tank. So that the air that's moving through the plenum is heated up by this hydronic coil, right? So it's easy to dump solar heated water into the furnace through hydronic coils. And if you can regulate the fan speed, you can circulate 100-degree air through the house, even 85-degree air through the house throughout the day, and you'll heat the house up to 85 degrees. So forced hot air is one of the least efficient ways to heat a house with traditional fuels, but with solar thermal, it becomes real effective because you can circulate air. You can take all the heat out of that solar loop. So you're coming down at 120, you're going back up at 95. So all day long, that collector is running at 95 degrees. That's perfect efficiency number for that. So forced hot air is a good candidate for solar hot water. Yes, sir.
How would you regulate the temperature in the house, like speed or volume?
Well, with thermal, it becomes it's a little trickier because I feel like in the daytime when the sun is out, I don't care about the house temperature. I want to take every BTU off that roof I can and put it into my house, store it in the chairs, the floor, the walls, the TV, everything. So the house temperature might get up to 65 or 70 during the day, or 75, but it's not gonna get up to an uncomfortable level. But you're better off storing that energy into the house, and so you have a broader swing of temperatures with solar thermal. And my house is no exception. When the sun's out, I got my pump running 100% putting it into that floor. And if it gets up to 68, 72, I set it at 60 anyway. But 68 might be still cold for some. But I let that go from 58 to 72 all day long. Just because you want to be able to collect it when you can. You don't want to say, well, I'm hot enough. Why don't you just put those on reserve for me later? Or put them right in the house quick. So that's one drawback to the comfort level. With solar heated homes, the most efficient way to do it is to put the BTUs into the house. The sacrifice is you get bigger temperature swings. You can do it by storing them in a storage tank, maintaining your temperature at the same, but that storage tank ends up costing you more money. And the whole idea is to save money. So, all right. So radiant baseboard, yes, sir.
I was gonna ask, when you're heating with air forced through a coil that's heated by solar, what do you pay for in efficiency for going through that heat exchanger?
Efficiency in terms of the.
In terms of it's a heat exchanger.
Yeah, well, actually, that heat exchanger is the end loop. So you don't actually have a heat exchanger between the collectors, and you're not going from the collectors to the tank, from the tank to the thing. You're going right from the collectors to that heat exchanger.
You're going from solar fluid to the air. You're losing something through there. You're not going to get every bit out of that heat exchanger.
Yeah, but it's not as much. I don't know. I think it would be less than 5%, because you're going right from. Everything's going out that plenum. If it doesn't go out the plenum, it's going back up to the collectors, and it's going to come right back down to try to get out again. So it's a very small amount. It's different than going from the collectors through a heat exchanger, from the heat exchanger to the tank, from the tank to the radiant baseboard. You're going direct. So you're already benefiting. Okay, and the collectors are a heat exchanger in themselves. Okay, so radiant baseboard, it's a very ineffective way to heat the home with solar. Why? Because the temperature set point is so high. The higher the set point, the lower the utilization of the collectors. Okay?
Can you explain that again?
Sure.
I thought that it was a good one, because you're putting 140-degree water into a mass of some kind, some concrete mass.
Well, radiant baseboard.
Oh, radiant baseboard, I'm sorry.
Yes, you're absolutely right. With the radiant floor, it's very effective.
Oh,
Yeah, because I can do 90 degrees works. But with baseboards, they require a higher temperature, which means that the solar isn't going to achieve that higher temperature as often.
But can you plumb it as the intake to your boiler? So
Uh,
that you have warmer water going into
Yeah,
the
so you plumb it as the return to the boiler is generally about 17 degrees less than the supply. So that helps by plumbing it. Put your solar tank in series with the boiler, so that it goes from your from the boiler to the home, from the home to the solar to the boiler, and that allows you to bring that temperature set point down by no more than 17 degrees. That's the differential between your supply and return on the boiler. But that's one way you could improve it. Yeah. Okay, so there's a lot of different ways to plumb into a radiant baseboard. This is one way. We got the collectors running into two coils on the bottom, right? This is a German German method, is to use multiple coils in the tank, because there's different zones of temperature inside the storage tank. They're called strata, and I want to dump into the most appropriate zone, right? I don't want a really super hot collector to dump into the coldest part of the tank, because I want it to mix with about 17 degrees less than whatever the collector temperature is. That way, at the end of the day, I still have a volume of water at the bottom of the tank that's cooler. That means that now if I charge the bottom of the tank, I can run till 6 o'clock at night rather than shutting off at 4 o'clock. You save a cold zone that you can keep putting BTUs into the tank. So you have multiple coils. The top coil is sort of an on-demand. This is a solar on-demand hot water tank for domestic. Cold water comes in on the top at well temperature, comes out of this coil up to 105 or 110, and right to the shower heads. And then the volume of water in the tank is what's circulated into the floor at 15 psi. So you're circulating the entire volume of tank water in through the floor loops, and you're separating the domestic through this coil on the top, right? And you have no issues with infection, Legionella, anything like that. They're separate. You have 200, 300 gallon storage tank, and that entire volume is what's being circulated through the floor. This is one of the newest ways to do it. I think I'll cross over this. Determining BTU load is important, obviously. Here's a couple examples I want to show you. There's a lot of different ways to mount systems. All right, and as I go through, you'll see. Maybe I like that style. I don't like flat plates, vacuum tubes. These are all systems that I was either designed or installed or commissioned or something. So here we have two banks of 3 in parallel. So these 3 are in series, but each row is in parallel with one another. This guy mounted them up off the roof for wintertime. This is in Drainback, Connecticut. He's a swimming pool, large vacuum tube system. Now you can't tell from this picture, but it's a Drainback. There's about a 12-inch drop from one side to the other. So during the day, the system gets flooded with water, and it circulates, putting heat into the pool. At night, pump shuts off, it all drains back, right? Big investment, but already he's got an indoor swimming pool, and his boiler hasn't kicked on since we put it on and commissioned it in mid-January. He's taking care of the whole load. This is a combi system, right? So up here you see the word combi system. That's what we refer to as a domestic hot water and heating. That's a combi system. I can either install a heating system, a domestic hot water system, or a combi system. All right. Combi systems generally have a lower solar fraction, all right, because the heat load is so high. So it's the combi system that we're in the 35 to 40% range. A domestic hot water system, we're in the 60% range. Okay. Here's a ground mount over near the Hudson River. Here's a non-pressure storage tank delivering to all 7 of his zones. Pull off that storage tank. He's got a radiant floor, but he also has a forced hot air zone. He has a baseboard zone. He also has a hot tub zone. All different temperatures pulling off that storage tank in a ground mount. Some people really like ground mounts because they're accessible. If you do vacuum tubes on a ground mount, you can swap out the tubes easy, easy as pie. There's no challenge there. So ground mounts work really well. There's no wind load, so they didn't, this is kind of a lightweight frame. They don't weigh much, and there's no wind load there. We did a system at Wallkill Prison, 600 inmates, and the state of New York wanted to. This was sort of the pilot program. They wanted to design a system for the inmates, so we designed the system with no storage tank. There's 1,400 vacuum tubes, and normally I said 2 gallons of storage per square foot. We should have had a 3,000 gallon storage tank at least. 3,000 gallon storage tank with 0 storage. And the reason is we looked at the load profile. Remember I said we had to look at consumption versus production? Turns out that they were using more BTUs during the solar day than we were producing. So we scratched the storage tank was like $10,000. We took that right off of the budget because there was no need for it. They're consuming more than we're producing. So that means that they're taking every single BTU out of these collectors all day, and these collectors are constantly playing catch up. Now, the only reason we could do that is because it was a prison. We're not taking vacation. They're not like, oh, I'm not going to take a shower today. You know, so we knew that it's very consistent. You wouldn't want to take a chance with a different, you know, you always have to have a storage. The storage tank is also not necessarily storage, but more importantly, it's a buffer. All right, it's a buffer. That's what it is. Most importantly, it's a buffer. All right, and this is working pretty well. This is a heating system. This gentleman is in the process of. There's no hot water load. This guy sells videotapes and refrigerators. There's no hot water load here, but he's installing an absorption chiller. Anybody familiar with an absorption chiller? Absorption chiller uses lithium bromide and 193-degree water, and it causes lithium bromide to move between states of matter, from liquid to gas to solid. Actually, it goes from solid to gas. I think it's sublimation, it's a refrigerant, and it's basically a way to refrigerate or cool the house or the building with solar thermal. You'll see them in the future, absorption chillers. All right, hot water system on a flat roof. Here's a church that we put this right into the furnace. As I was mentioning, we go right from the collectors to the furnace, right into the basement. So all summer long, the humidity level in this church basement went down to 0 because we're blowing hot air into the basement of the church. So all winter long, the hot air just rises up into the church. In the summertime, it's so cold and damp in that basement that you don't feel any effect of the heat. It's just dry down there now. So that worked out pretty well. Some of the clientele of the church weren't too happy
You're
with it.
saying that the boiler is just like a heat sink? It's somewhat of a radiator down there, just the boiler?
This is tied into a furnace,
Oh, it's a furnace.
and we're blowing hot air across the coil.
What about in the summertime?
That's what happens in the summer. The heat from the roof is going into the basement through the air hydronic coil, and it's delivering dry air
It's passive.
through, and it dries the basement out. Open the windows, and hot, moist air leaves the basement.
Does that overheat the rest of the building?
Doesn't.
Doesn't.
No, because the windows are open. There's not much airflow between the top and the bottom. That's why it was so moist and damp. And so open those windows, and the hot, moist air quickly leaves the building. The result is that the timbers dried out. It was really quite something. I remember, putting the thing in there. You could see almost like, mold on the timbers. Gone.
What does that basement feel like when you're in the basement?
It felt like a normal. Most basements are nice. You get a chill. A nice dark. This didn't have a chill to it, but it wasn't. Humid. It was. You could tell it was drier. No, not at all. Nope. Here's a flush mount. All right, 5-person home. There's 50 tubes. Incidentally, 1 tube is equal to 1 square foot. Okay, so 1 tube is equal to 1 square foot. So in other words, 10 tubes per person. All right, 10 square feet per person, 10 tubes per person. This works. It actually does it does heat as well, but I don't think they got much out of that. They could have spent the same amount of money and insulated their ceiling and had a bigger impact. But domestic hot water is a good one. Now this guy, you see the white? Here you can tell. He painted his shingles with Sherwin-Williams highly reflective roof paint underneath the collector tubes, and he got 17% more out of this system than what was calculated. And the simulations that are done are always within 3%. They're really, really good simulation software. And his was just an anomaly. And he's telling us, and then he sent us this picture. We didn't know that he had painted the roof, and that's what it was.
Explain that before. Why is that?
Well, where's the tube? Anybody? Yeah. Here, you can throw it to me. I'm just kidding. Yeah, you get because where's this facing right now? Is it? It's not. It's 360 degrees. So if anything passes to the side, hits the roof, hits the shirt, bounces up, hits the back. So basically, you're increasing the absorber area that's exposed to the sun by increasing the reflectivity behind the tube. It works. It's effective. Oop. Okay. So here we have a nice balanced system, very symmetrical. We got 5 collectors on the bottom row, 5 collectors on the top. Now there's a way you can plumb this, and it's called reverse return. But if I didn't plumb this in reverse return, then I could use balancing valves. But the bottom line is, you got to make sure you have the equal flows through both collectors. Okay. Now, here's a homeowner who decided he wanted a solar thermal system no matter what. Well, his house wasn't necessarily facing the right direction. But this was early on. Knowing what you know now, what if, for those of you who are at the beginning, and you know the losses, his roof was facing east and west. He could have chosen one of those, east or west, and so he's got 4 collectors. The loss, remember, was about 23%. So if he added one more collector, and one with one side of the roof or the other, the outcome would be the same. All right? So you always have to consider aesthetics. For the good of the industry, please consider aesthetics. Because you might not think, you say, well, hell with everybody, I want to put it on my roof this way. But you know, the reality is, you gotta think long term, and who's gonna see this besides everybody that drives by? And who's gonna say, "Yeesh, I don't want one. I don't like those solar collectors," you know? Anyway, now overheating is a very common issue that everybody that installs solar thermal and people that know about it are concerned with overheating. I'm not so concerned with it anymore because I know big expansion tanks will take care of that issue of overheating. The collectors can't overheat. The issue is making sure the collectors can empty properly. Once they empty, they don't have to overheat. But this guy installed his arrays. This is a heating system, but he built a little roof here so that when the sun is low on the horizon, it's exposed to both of those collectors. Boom, they both get it in the wintertime. But as the sun moves up, and you know, we're looking at 75 degrees zenith, this top roof shades the bottom roof. So he was able to reduce his production in the summertime by shading the bottom rows with his mounting frame. So it was a great idea, but knowing what I know now in terms of actual overheating issues, all you have to do is get a big expansion tank, put it in the right spot, and you don't have to worry about overheating. But it's still a good idea. This guy installed it himself. He didn't even have any idea what he was doing, but he did his homework. He was very meticulous to how it had to be. He's got a car wash, laundromat, and ice cream parlor. A car wash, laundromat, and ice cream parlor all tied into the same system. He started saving $700 a month. That's what he was paying for fuel oil for his hot water. And the system paid for itself in under 2 years with tax credits. And he, you know, I mean, and it's still, it's a Drainback. So it's a really well-designed system, and it's 5 or 6 years now. He's probably saved, I don't even know, $30,000 or $40,000 savings. And the thing about savings is, it's tax-free. If you save $1,000, that's tax-free revenue. So if you save $1,000, what would you have to actually make in order to increase your salary by $1,000? You have to make $1,500 or more to get $1,000. Well, you get $1,000 tax-free. Another thing about the price, and I thought about this as I was, you know, I used to sell systems for a company about 4 or 5 years ago, and I would always say, well, you know, now's the best time. Well, it's always the best time, right? You had a used car. Now's the best time. But after about 4 or 5 years, I start looking at some of the older systems, and I see some of the invoices, and I see, well, they paid $2,400 for the storage tank. Well, now that storage tank is $3,600. And so if you think about how fuel costs are going up, well, the savings that you're going to get are relative to fuel costs, no matter when you install the system. But when can you install the system at the lowest cost? Now. And so as fuel costs climb, everything climbs. And solar's no exception. Transportation, I mean, all that stuff, all right? The cost of the installer is going to go up because his costs go up. So it really, truly is true, and I've observed it. The best possible time to invest in anything is when the price is at the lowest. And right now with thermal, the price is at the lowest. You see, and don't confuse the two. Photovoltaic prices can skyrocket because they're a commodity. Warren Buffett can dump $400 million into the system when the next day the cost goes up. All right, the Koch brothers, after Solyndra got their secured loan or grant from the federal government, you know, the Koch brothers and their subsidiaries spent $250 million and bought all surplus panels. And the next day the price of the panels dropped. Why? Because the Koch brothers had a large holding of that commodity, and they were able to fluctuate the price. And so now Solyndra, which is this company that Fox News got on for, you know, making solar be a terrible investment. Well, Solyndra had a warehouse of product that they couldn't even sell for what it cost them to manufacture because the Koch Industries had bought all the surplus and brought the price way down overnight. You're not going to pinpoint them to that, but that, you know, that's anyway. But solar. My point is, solar thermal is not a commodity. The prices aren't going to just go up and down. They're going to slowly keep going up. Manufacturing costs can go down a little bit, but not much. But the big cost is installing costs, right? And installers are not making a lot of money right now. They're taking hits because, yeah, I mean, they're trying to make a presentable case and make it cost effective, you know, and you can't gouge people that are trying to save money. That doesn't work. So, really, truly, the best time to install it was yesterday. The second best time is right now, because it's going to happen. The prices of every single thing are going to keep going up. And the nice thing is, there's without investing in ExxonMobil or investing in Shell or any of those companies, what's the second best way to invest in energy? Become your own energy provider. Because if your savings is $1,000 now and the energy costs go up 20%, then your savings is $1,200 next year. They go up 20%, then your savings is $1,500 the next year. So your investment return goes just with energy costs, just perfectly in line with the rising energy costs. That's going to be your return on investment. And that's unknown. It could go up 4%, could go up 400%. And if it goes up 400%, you're not going to be able to afford solar. You know, you're not going to have that luxury of, you know, saying, okay, let's put $7,500 down. We're going to save $700 just to heat my house for the winter. So, but you don't want to do it out of fear, but you know, the motives for people that go solar are really wide. You know, you got the far right, who's just penny pinchers and misers, and they look at it as a strict investment. You got the far left, who are just want to do it just because it's the right thing to do, and they got everything in between. And incidentally, a lot of the clients that I've dealt with are older folks. I would say comfortably that 7 out of 10 are older, maybe even 8 out of 10 are older, even retired people who have wanted to do it for a long time, and now at the time's right. They have a little bit more expendable income than younger folks do. So, you know, 7 or 8 out of 10 people that I've dealt with that are in solar, most of these houses, this guy's retired, just to show you, that's a retired teacher. This is a retired pilot. Don't know that guy. He built his house. These are both retired. Well, he's not retired. Well, anyway, just to, you know, that's, yeah, not quite. And so here's another one in Ulm. It was real interesting walking around Ulm, and there was just all the homes. I just couldn't believe it. It wasn't like a special, like, oh, cool, you drive around the hill, you see, oh, look at that awesome house up there. It was every block. It was every house was like designed just for that purpose, right? And so we got to get there. We're not gonna make a big difference until the building technologies really buy into it.
Well, good. That segues into my question, which is, most of what you're talking about is retrofitting existing homes. What if you started as a planning and construction phase of doing this type of technology? What would be the possible diminution of cost as well as the efficiency of the system itself? Because you're going to design the house or the building to support that type of
Yep.
technology.
That's the best way. In terms of numbers, it's tricky, but I can tell you my experience. I built a house specifically for solar heat. All right, and I got about $12,000 worth of materials into the solar portion. and the incentives that I got were about half of that. All right. So after 2.5 years, my neighbors are spending about $1,500 to $2,000 a year for heating oil and all that stuff, and I'm at 12 cents a day. So my system will be completely paid off probably next year, and then for the next 25 years, it's nothing. So obviously, building it for that purpose, and I can circulate 90 degrees from my roof, which means my collectors can operate at a much higher efficiency. So if you retrofit, then you lose collector efficiency. You have to settle for a lower solar fraction. Yeah, we can't just swap out everybody's houses, but I think the biggest up and coming industry is going to be, conservation retrofits, insulation.
Do these vertical panels work? How is their solar efficiency?
Well, this is going to be a heating system. Now I'm walking down the street here, and I said heating system. I didn't go knock on the door and ask him, is that a heating system? But how can I infer that this is a heating system and not hot water? The angle, because that steep angle in the summertime, the sun is up here, it's hardly getting anything on here. But in the wintertime, the sun's down here, right? So I know that this is a heating system because that's what these are angled for when the sun is low on the horizon. Okay.
So is that a south-facing building, or?
Yeah, I would say, I can't recall exactly, but I would say pretty darn close. But this was no exception. It wasn't, it was really something to see a city that was designed like that. Here's an example of YMCA, and these collectors are sitting on this gravel roof on these concrete blocks. One important thing to know about vacuum tubes is the wind load. If this was flat plates, we'd be bolting them to the frame of the building. We'd need an engineer to stamp it. As soon as you involve an engineer, things get real complicated. All right? So we didn't have to worry about that. We just put them on these concrete blocks because there's no wind load. Makes the install real simple. Here's an off-grid guy who's got 2 thermosyphons. And you notice the PV, this is a cord home in New Berlin, New York. This guy with a photovoltaic panel in between the thermosyphons. Harvard University, as I mentioned before, colleges are just going all over this because the students want it. Committees all across the country, the student committees are pushing for it. And the dean says, yeah, that's a great idea. They're generally progressive anyway, so they say, let's do it. Let's get it. So colleges all over the place are doing domestic hot water systems. Unfortunately, their load profile isn't consistent with the production because, summertime everybody leaves and all of a sudden the collectors start really cranking. So you have to, design it for a dormitory that's going to be in use in the summertime. This was my house, and this day, I can remember this vividly. My favorite hobby is to stand outside now and watch my snow fall off the collectors. After we get about 2 inches of snow at night, and I go outside in the morning, the sun's beating down, and I'm watching them, and I'm just staring at them, and it seems to take forever, and they start to crack, and then pretty soon, and then I run inside, and I see what the collector temperature is, and you can see it just the digital numbers climb. So we're talking about 15 degrees outside, right? It took about 5 minutes of sunshine, and this was like 8:30 in the morning. Starts climbing down. Now I'm pushing 120 degrees. 120 degrees is coming into my floor at 8:30 in the morning, and it's 15 degrees outside. All right.
How big a snowfall was that?
Pardon?
How big a snowfall? 6
That
inches?
no, that was 2 inches of light snow at night. Yeah, and I mean you can tell that the sky, it's not like a stellar day here, which is important because I don't even have a boiler or a furnace, so it's a big deal. When the heat, when the sun comes out, it's important.
Fireplace?
I do have a small yodel. It takes 10-inch chunks.
Yeah.
And I burned about 2.5 face cord last year, which was it's not that much.
Got one little useful point to add here. It depends on the angle, because I've built them at 40 degrees and the snow falls up. And if you go down to 38 degrees, it sits there.
Yeah, that's true. Well, and if they're at 38 degrees, then it's going to take a while. Vacuum tubes, they're not even going to. Vacuum tubes will have snow on them for 2 or 3 days. Let me just go back really quick. I'll show you a picture to kind of visualize what I'm talking about here. This is my folks' house. In the wintertime, this entire roof is melted, except this white patch on the center of the roof, and that's the tubes. So if you can picture the opposite of what you would think, the entire roof is melted, except this rectangle of white snow on the roof, and that's the tubes. And it stays like that for a couple days. They don't end up losing that much anyway, because the sun passes through the snow anyway. But I'm in the process of building this long solar wall. This is a concrete board, and I painted it flat black. All right, so we got about 32 feet, 4 feet tall, of concrete board painted cheap Home Depot flat black paint. And on a day like this, I go out and touch it. It's 100 degrees. It's 15 degrees outside, but the wall. And if I go along the side, I can see the waves moving up the windows. So not only that, but it reduces my heat loss out of the windows now because it's been working really well. Okay, things that can, yes sir.
Question for you. Can you put the panels with the tubes running horizontally, or do they have to be going?
You can't with the heat pipe tubes. Now the gentleman down here
You can or can't?
cannot.
But what about
This style here, this is a vacuum tube that is called direct flow, and we're pumping fluid down here. Okay. Now this style, we can mount like this. We can actually mount it like this. Come out flat like this, okay, because you're pumping the fluid any which way you want. But with there's the heat pipe style, which is what the gentleman has down here, a big heat pipe collector, that relies on convection. And it has to be mounted at an angle of at least 15 degrees, no more than 75.
what about the flat plate?
Flat plates, it depends on the manufacturer. A lot of them have ventilation issues. So if you don't allow for moist air to move through the collector, you'll get condensation. All right, so some manufacturers design specifically for flat or flush mount. So you have to check with every manufacturer a little different, but most of them require a certain pitch to allow for ventilation inside the collector. All right, so that's going to be manufacturer specific. Good question. Okay, for those of you who are going to do it themselves, you're going to save half the cost right up front. Installation is going to be half, all right, and it's not out of the realm of possibility. I mean, I've had an 85-year-old guy come. He bought the stuff. He said, "I'm doing it myself," and so he wasn't a plumber. With a flexible line set, with a pump stations, it's much simpler than it used to be. Okay, you don't have to solder. You don't have to sweat. Well, sweating, but you don't have to solder. Another thing you want to consider is, do you have any solar potential? The first thing is, how much solar potential do you have? Okay, you can't say, well, I want a system with 180 square feet of collector. That's what I need. So then you start doing your work. You realize you don't even have that usable area. So what is the potential? And potential is not only the roof area, but your orientation and the pitch of the roof. That's going to determine potential. Okay? Do you want thermal or do you want photovoltaics? Talk to a photovoltaic guy and he'll say that's the best bang for the buck. Talk to a thermal guy, thermal's the best bang for the buck. All right? But eventually you'll come to your own decision. What's better for you? All right? What subsidies do you have available for you? One thing I can say, if you are apt to do it yourself, you're not going to be able to do PV yourself. You have to have somebody sign up, interconnection. You can't tie into the grid, you go to jail. You can't just, it's a federal offense. You got to have somebody, and you have to pay that person to do that. With thermal, anybody can do it. All right? These two kids over there, my kids, they've done it. I've had them on jobs and working and doing that stuff, and eventually they'll be able to do it. You don't have to have any necessary certifications. There might be some municipalities that require a plumber to tie into the domestic load, but generally you can do most of it yourself.
So what do you think about that controversy between PVs and heat pumps versus solar?
Thermal?
Yeah. The one for the HW.
Yeah, I mean, I don't buy it at all. It's hands down, thermal is the way to go. Heat pumps are a great technology. They still have to, but it's still more. The payback isn't there. There's more points of failure. You know, and also you have to fill your whole roof up. You know, if you see somebody with one or two panels on their roof, there might be power in the refrigerator. They have to fill their whole roof up with panels. With thermal, you get 70% efficiency versus 15%. So 10 square feet per person versus 50 square feet per person. You know, you get 5 times the value. PV can last a lot longer though. You know, a lot of reports you hear that photovoltaic panels will lose efficiency, and you know, we say, well, okay, 20 years, 25 years, because that's really the experience we have. But there are estimates that they'll produce electricity for 100 years. You know, there's 100-year-old houses that still current is passing through them. You know, that's all. So these panels have enough silicon or whatever else is in there. They're going to produce electricity for 100 years. We just can't say that for sure because we don't have any around 100 years later. But thermal is the way to go. It's more accessible for everybody. You know, heat pumps I think is a great solution, but it's too costly. I think. Using the SRCC collectors, I just want to go over a couple of features and benefits. That, you know, solar hot water is a very mature product. It's not something that's new. It hasn't just come around. People say, oh, let it work the bugs out and all that. The bugs have been worked out. You know, and there's also installers that are trying to invent their own systems. Say, oh, well, that guy better work his bugs out. But if you do what they've done in Germany, and I'm a big fan of doing what's already worked. To me, the proof is in the pudding. If it's worked for 20 years, what do we need to prove? You know, so it's not at all new, and it's hardly technology. Actually, it's just converting sun to heat. Tubes versus, you know, you have to consider tubes versus flat plates, the selective absorber, the blue versus the black. You know, the benefits of each of these. Basically, the most important thing is installation can be done by most DIYers. I think the only way, remember I said there's about 11 million hot water heaters. There's 110 million hot water heaters in the US. 10% of those need to be replaced. If we wanted to reach market penetration like they did in Germany, 1 out of 3, that would be 33 million hot water heaters. That's a 1 out of 3, similar to the way Germany is. If we were to reach that with the existing installer crew, all right, let's say there's 2,000 installing teams in the country, which is probably not even close. There's probably more like 500 competent, and there's probably 200 experts. You know, I would say, just from my experience, a lot of people have done it, but anyway, nevertheless, if we were to achieve that with 33 million, and they did one every single day, you know how long that is? It's 1,500 years. I did the math. It would take 1,500 years for us to reach the same market penetration as they are in Germany. So what has to happen? Our installer base has to explode, and the system installing has to get more efficient and compact. So the only way in my mind that it's ever going to happen is if you have plug-and-play systems that anybody can put onto their house. You know, $3,000, you put it together, put it up, take it down. If you rent, put it up, take it down, take it with you. That's the only way it's going to happen. And I see that happening pretty soon, a couple of years. But that's the difference with solar thermal and PV.
Does that exist, what you just said?
There's some, yeah, there's some that are out there. In fact, the guy who made that wand, wherever that went to, he has a neat little system that, you know, it's all user-friendly. He uses hose clamps. You know, I have a 1988 Ford pickup that has original radiator hose in it. You know, so a lot of people say, well, radiator hose, that's not going to last long. Well, what if you had some high-temperature, high-pressure radiator hose, and you used bibs, brass bibs with hose clamp, and you could just plug this into the pump station, run it wherever you want. You don't have to have any. You don't even have to have a wrench. You have a screwdriver, right? A clamp, you know, for a valve. Do you need a $45 brass valve? No. Harbor Freight, for this stuff, you just get one of those gate things that just screw down there like $2. A vice grip could work as a valve, right? So the old, you know, the old traditional copper, stainless steel. When I say old, stainless steel is new to the American market, but I think it's going to be phased out. And we're going to use, you know, high temperature radiator hose with everything included, very simple and easy. plug and play. I'm thinking of some fittings like your compressors, where they come on the compressor, then you pull a ring back, and you have bearings in it. So you can just plug it in, all right, and then take it off when you want. You don't have to turn any wrenches. So if you're thinking about doing it yourself, start looking into it seriously. But it won't be very long where the systems will be. That's why they don't have them at Home Depot and Lowe's. They're at Home Depot and Lowe's knows. They're just waiting because somebody's going to come out with a kit that revolutionizes the installation process.
But the subsidies are sort of like in Vermont, you have to be part of
certified.
the solar mafia in order
Yeah.
to get
Yeah,
that.
they don't cover DIYers.
The state incentive, but the federal incentive of 30%.
Federal's fine.
It's pretty
Yeah,
significant.
but if you could save half the cost and use the subsidy.
That's very true.
Well, okay, but why have it at all then? If you're, why should a homeowner be any less, able to get that subsidy than,
Well, because you have to have a bureaucracy.
Yeah.
nice?
The subsidy has to answer to the quality.
It goes back to the Carter days. During the Carter days, I was doing it, and there were a lot of fly-by nights, and there was a lot of bad stuff done. This is, I think, the pendulum's swung the other way. Do you agree with that?
Oh yeah. They don't want to. They learned their lesson. They doled out a lot of money, and the system's failed.
Right.
So now NYSERDA, which is the equivalent for New York State, they're offering a lot of money, but they're very, very tough. The inspection process is anal, and it's just ridiculous. But they got burned back then, and they don't want to do it again. So the solar incentives. If you haven't visited desireusa.org, this is a really, really good website for all types of renewable incentives. It's a database of interstate renewable incentive program or something like that. But there's real obscure grants. The father of a left-handed carpenter who lost his right thumb gets $50 deduction for all solar. It's just weird stuff that but anyway, visit that because municipalities, they don't necessarily promote this program, but they're obligated to, so they have it. They don't want to give the money away, so you have to go out and find it. And the 30% is total cost. All right. So if the system costs $8,000, you're getting $2,400 back from your federal tax credit. If you don't owe taxes, you don't get anything. It's not a grant. It's not a rebate. It's a credit. So if I paid $2,400, I get $2,400 back in the form of credit. All right. But it's pretty significant, and it rolls over for 5 years. So if you don't owe $2,400 the first year, you get what you owe back, and then the next year you get the balance for 5 years. The federal tax credit is scheduled to be up for 2016, and I don't know. I have no idea. I can't even guess if they're going to continue it or not. All right. Production credits, and just point out. Yep. There's a lot of local programs. The Vermont is an excellent one, but you have to be on the list. But in terms of production credits, the carbon cap and trade, if you put a system on your house, every 25 square foot is roughly 1 ton of carbon dioxide. All right, and so you can earn these carbon credits. Right, so you got people that are leasing systems. They own the carbon credits. The value of those carbon credits right now is virtually nothing. But the legislation is still there. Once those carbon credits are traded on NASDAQ, the price of those carbon credits goes up, and it's an annual reimbursement. Right? So if you put that in your file, because eventually you'll be able to cash in. That's actually all I got. So I don't know if I finished early or not.